to hit record on this one as well. And so what this means is that if you think of it as like a car company, for example, is if your enzyme is at factory where you're going to be making lots of cars, it means your assembly lines are completely filled. You can keep adding more money into it, but you're not going to be able to make any more cars, make any more product because it's as full capacity as possible. And so the limit that approaches is called what? That's Vmax. Here, let me change the color here so that way. It's Vmax. I'll just write it up there. And the way that Vmax is related to the the turnover number is that Vmax is equal to what? How is that related to the turnover number, which is kcat? Right, it's kcat times enzyme concentration. That's why if you know the actual enzyme concentration, you can figure out the actual rate constant, which is called kcat. Okay, many times in vivo, though, we don't have that luxury, so that's why they'll just use Vmax instead. But in vitro, you may have that luxury, and so you can get it down to the exact rate constant. All right, and so then we have this, change the color on it, where if you go to 1/2 the Vmax, and actually quite a few people got this part right, and you go over to where it hits the function, and then you look down on the x-axis, you get this Km. It's called a Michaelis constant. It's actually a little bit more complex than what you would, than what your book probably explains it as, but mathematically complex. Visually, it's quite simple to look at, because technically the amount of substrate you need to get to 1/2 the Vmax. But it's sort of like a barometer to use if you're trying to have the same enzyme and compare two different substrates, or have the same substrate and compare two different enzymes, just to see the relative affinity. It doesn't tell you anything about how fast or how efficient it is. It just tells you, relative binding. In the simplest of enzyme schemes, it really is the binding constant, but for most enzymes, it's not. It just gives you an idea of it. Okay. Then we have what many times is considered, it's the most difficult to define, yet it's also, in many ways, the most important. And that's the catalytic efficiency. This is how efficient it is. And that's the kcat over Km, if you know the enzyme concentration. Otherwise, it's called Vmax over Km. And so that's why, technically, it's the slope of the tangent down as it gets towards 0. So the slope of that, whatever that color is, the slope of that line, which I'll have to, so I'll say M, and that's equal, in the Michaelis-Menten, it's equal to Vmax over Km. And it's always going to be, a second order rate constant. So it has those really, really weird units usually that are kind of difficult to understand, like per molar per second. But it's the one that literally will tell you how efficient it is.
What is that?
Pardon?
What is that, the yellow?
That's the slope of the, so that's the tangent. If you think back to the, back to calculus or algebra, the tangent as it approaches 0, it's the slope of that line, technically.
What does that indicate? Like,
It's called the catalytic efficiency. It's also called the specificity constant. Okay, but a lot of times they'll just say Vmax over Km or kcat over Km. Okay, so the reason why, let me go to another one and I'll redraw part of this because otherwise it's going to get too messy. For example, let's have two different, not black, because black on black wouldn't work very well. So if we have this one enzyme,
It's not connected.
okay, awesome. It still says it's gaming and streaming, which I don't like that one, but 1 over V versus 1 over substrate concentration for the line Weaver-Burke. And that's without, the white is without the inhibitor. And just to review, this, which one person on their quiz, like they verbally wrote out, oh, the y-intercept will be 1 over V max, but then they thought, they switched it with on the graph with what the x-intercept is. And so this is 1 over V max, and this is negative 1 over Km. And of course the slope there technically is Km over V max, so you can take the slope and just take the inverse of the slope and you can get the catalytic efficiency that way. But the uncompetitive is really easy to tell because since the Vmax over Km is the same, so will be the Km over Vmax, and so it's a parallel line. Well, that is not a parallel line. Oh, it's not gonna let me. Oh, sorry, I just broke that one. That's better. But, so that way, it would have the same slope, but it's gonna have different Kms and different Vmaxes.
Which one is that?
That would be for the uncompetitive.
What is the white one?
That, the white one would just be like normal. Yep. It changed both 1 over Km, both 1 over Km and 1 over Vmax. Right, because it's now, this is now the new 1 over Vmax, and this is now the new negative 1 over Km.
And we're gonna have to know the x-intercept, y-intercept for the test, correct?
Well, I mean, that or if you know the formula, you can figure it out. Or if you know the y-intercept and the slope, you just need to know 2 of the 3 in theory, because you can figure out the third thing. So, or if you know the formula, because it really is mathematically just the inverse of the hyperbolic formula. And so, yep. So that's why you just kind of practice with these kind of questions. It's very important, and really this is the only class that really delves into it unless you take enzymology class. Okay, so I will go ahead.